Morning, all.
Morning.
Morning, all. Oh, everybody's here. Hi, Jeremiah. Can you hear
Good
me?
morning.
Good. You can hear me at least. Good. I got 22 people in here. Wow. Lots of people that are waking up. Even me. Give me another half an hour. I'll be wide awake. How we doing today, guys? Any problems? Any issues? Jeremiah,
I'm not sure if I'm.
Go ahead, Corey.
Well, you can hear me. I was going to say I'm not sure my microphone's working, but I am now.
Okay. Jeremiah, you had an issue. Did I solve it?
I had an issue. What?
Didn't you email me something? I can't hear you, Jeremiah.
You can't hear me?
You keep on muting and unmuting yourself. Right now you're muted.
Oh, that's weird. All right, there we go.
Everything okay?
Yeah, everything's
All right.
great.
I thought there was an issue. Anybody have anything else? Okay, guys, this is part of today's lab is the same thing we did last week. The hydrate thing, you remember that? So we're going to be doing, that's the first part of this lab. The difference is we have to treat the molar ratios just a bit different for the waters than we do for the subscripts. And I'll try and explain that when we get to that point, okay? Now I got to share screen. And is everybody seeing the slideshow?
Yes.
Thank you
Yes.
very much for responding. Okay, so basically, if I'm looking at a mole's worth of magnesium chloride, this means I have 6.032 times 10 to the 23rd atoms of magnesium and 1.2 times e to the 24th atoms of chlorine, right?
Yes.
Right.
So basically, if I'm going to divide them by the Avogadro's number, I'm going to get 1 mole of magnesium to 2 moles of chlorine. So in effect, what I'm trying to say is when you look at the subscripts for any chemical formula, actually what those are the molar ratio of the atoms to one another. Does that make sense to you guys?
Yes.
So if you're doing an empirical formula problem, any empirical formula problem, I'm going to get to this at 5:30 tonight. If you're doing any empirical formula problem, the first thing you do, find the masses of all the elements. And that is going to be the hardest job for you to do because everything flows right after that. Turn all the masses. You got all the masses of the elements? Divide by the atomic weight, turn all those masses into moles. Because remember, we said there is a molar ratio between the elements. There is not a mass ratio between the elements. Then, third step, once you have all the masses in the moles, look at the moles. Find the one that has the smallest number. Divide all of them by that smallest number. If after you do that, you end up with a fraction, use a multiplier to get rid of the fraction. For example, if you have a ratio of 1 to 1.25, you multiply by 2, that becomes 1 to 2.5. You haven't gotten rid of the fraction. You multiply it by 3, that makes 1 to 3.75. You still haven't gotten rid of the fraction. Multiply it by 4, and you get 1 to 5. Or more importantly, you multiply both ratios by the 4. So instead of having a 1 to 5 ratio, you have a 4 to 5 ratio. Is this making sense? And is this kind of reminding you what's been done in the past, guys?
Yes, sir.
So empirical formula problems. This is the strategy we're going to use to work them. Okay. What we're doing this lab, we're finding the empirical formula, not of iron bromide, but of copper chloride, .ZH2O. What we need to find is we need to find the numbers X, Y, and Z. To do that, we've got to find the masses of the water, the iron, and the bromine. Water's easy. Didn't we do that last Thursday? We took the sample, we weighed it in the crucible, we got the weight of the hydrate. Then what we did was we weighed it after heating. Subtracted the two, that was the weight of our water. Simple, easy peasy. We've done that before. Now we have the anhydrous sample. Larry, if I've got this compound, FeBr.ZH2O, and I've driven off all the water, what is left?
The FeBr.
Just the iron and the bromine. We're going to use that in a second. So again, if I've got the mass of my hydrate and the mass of the crucible, I can subtract the two. I've got the mass of my hydrate. Mass of the crucible and anhydrous, subtract the weight of the crucible. I got the weight of the anhydrous. Now I've got two ways to make the weight of the water. Let's see, Marvina. Can you tell me one of the two ways I can find the weight of water with this information I've got on the screen?
The mass of water lost.
Tell me how I do it, or tell me the numbers I subtract.
Subtract 25.785 minus 25.164 grams.
Perfect. You're going to subtract the weight of the crucible and hydrate and the crucible and the anhydrous. Perfect. That will get you the weight of the water. Let's see if somebody else is paying attention today. D, you there?
Yes.
Okay, T. Marvina said that one of the ways I get water is subtract the mass of the crucible and hydrate and the mass of the crucible and the anhydrous. Can you tell me another way to get the weight of the water?
The mass of hydrate, subtract the mass of anhydrous.
All I'm going to do, I've got the weight of my hydrate. All I got to do is subtract the weight of the anhydrous. Both ways. It doesn't matter. You do both of them, they will give you the same answer. Okay? So we got first of our three things. We've got our water. Now, we've got to somehow separate our iron and bromine. We know what the iron bromine mixture or the iron bromine compound by itself weighs. We got to either isolate the iron or isolate the bromine. We're going to use our friend, the single displacement reaction. We're going to put a metal into a solution of iron bromine. We're going to put a metal in there that's more active. And just like the Flintstones, guys, if we have Barney and Betty being my iron Br compound. If I have Barney and Betty and they run across Fred, Betty's looking over and says, hey, Fred looks a whole lot better. I don't like this short little dumpy blonde guy. I'm going to go for the big husky brunette. So Betty dumps Barney and we have a new couple, Fred, Betty. Barney is off crying on the road somewhere as roadkill. It's the way life happens. Life happens to people that way. Same thing happens to chemicals. Aluminum is a more active metal than iron. So if I put aluminum in a solution of an iron salt, the aluminum is going to give up its electrons. It's going to force them onto the iron. And the aluminum will be ionic. The iron will end up being neutral. Let me draw another example. I'm a drug dealer and I have my little flunky. I see Mr. Customs Man up there. Am I going to dump my kilo of cocaine on my flunky so that the flunky can take the risk and I'm just going to walk through, right? Isn't that what happens in real life? Same thing is happening here. Aluminum has the power to shove its electrons onto iron because it is more active. Because it's more active, it will end up ionic. Bottom line here is, haven't I now isolated my iron? So if I've isolated my iron, I can pull the remaining aluminum wire out of my solution, and I've got iron, solid iron metal. Iron metal doesn't dissolve in water, so it's in there as a solid. So all I got to do is filter out that iron. So I'm going to weigh a piece of filter paper. Then I am going to put my solution through this filter paper, and the iron will stay back. Everything else will go through. Dry out the filter paper and weigh it. I now have the mass of my iron and filter paper. Subtract the weight of my filter paper. I now have my weight of iron. So Taylor, how am I going to get the weight of my bromine? Do I have another piece of information? Got to unmute yourself, Taylor. There you go.
You said you needed another piece of information?
I've got another piece. I've got the weight of my iron. I have another piece of information. What can I use? I don't know, Taylor. It's a perfectly good example, good answer. If it's not obvious, then this is the
You
first time you
heat-
had this. There's no reason
heat
for you to know.
it?
What's that?
You heat it?
I've already heated it, and when I heated it, what did I get the weight of?
The hydrate?
No, I didn't. The weight of the hydrate was before
The
heating.
anhydrous?
When
After
I
you
heated it, I got the weight of the anhydrous. Now, Taylor, what does the anhydrous consist of?
The salts in the solution?
Nope, not the salt in the solution. Maria, I have the anhydrous weight. What does the anhydrous weight consist of?
The amount of water lost.
Nope. That is I can get the amount of water lost by subtracting the anhydrous weight from the weight of the hydrate. That's part of what I did already. But what is the anhydrous? What did I say the anhydrous was composed of?
Iron and bromine.
Iron and bromine. Okay. So, Elia, if my anhydrous weight is the weight of my iron and bromine, and I just went and found the weight of my iron, how do you think I'm going to find the weight of my bromine?
Subtract the two numbers.
The weight of the anhydrous is iron and bromine. I just found the weight of my iron. I subtract the two, and I get the weight of my bromine. Now I've got the first part of my empirical formula solved. I have the mass of my water, I have the mass of my iron, and I have the mass of my bromine. Kylie, what do I do next?
After all that,
After I've done step one, what do I do next?
turn the masses into moles
How am I going to do that, Kylie?
by Multiplying by 6.02 times 10 to the,
Nope, what that will do is that will give me atoms. I don't want atoms, I want moles.
Molar ratio.
No, I don't know that. I'm trying to find the molar ratio.
Divide by molecular weight.
I'm going to divide by the atomic weight. So I have the weights. I have the weights of all three of my substances. I have my weight of iron. I have my weight of bromine. So what I'm going to do is I'm going to divide my weight of iron by the atomic mass. And I end up with 0.00575 moles of iron. Next thing I'm going to do is I'm going to take my bromine weight and divide that by the atomic weight of bromine. I end up with 0.1722 moles of bromine. Now, Adrienne, I've got the moles of everything. What do I do now?
You divide them by the smallest number of moles.
Adrienne, between iron at 0.00575 and bromine at 0.1722, which one is smaller?
Iron.
Iron is smaller, so I divide by the 0.00575. I get 1 for iron. I divide the 0.1722 by 0.00575. I get almost 3 for my bromine. So my molar ratio, whoever mentioned molar ratio earlier, this is how we've determined our molar ratio. I've got a 1 to 3 molar ratio. And what I said earlier is that the subscripts are the molar ratio. So the subscript for iron is 1. The subscript for bromine is 3. Does this make sense to you guys? D? Is it making sense to you? D? Do you understand this?
Yes, I understand this.
Alexis, we good?
Yes.
Monica?
Yeah.
Jonathan, we good with this? We good,
Hey,
Jonathan?
Can I see like the original formula we were looking at?
I'm sorry, the original formula, the original
it
set
was,
of 4.
huh?
My instructions, is this what you want?
Yeah. No, go back. No, not that. The FEBR. What is the Z?
They're all numbers. Okay, Jonathan, some salts exist as something called hydrates.
Okay.
And what happens is they incorporate some water into their crystalline structure. But they incorporate water into that structure at a molar ratio. There's going to be 1 mole always 1 mole of the salt to a number of moles of water that's incorporated into that crystal structure. Does
Okay.
that make sense, Jonathan?
Yeah.
So literally speaking, we're looking at 2 molar ratios. We're looking at the molar ratio between iron and bromine, which we just determined was 1 to 3. We're also looking at the molar ratio between the salt and however many moles of water there are.
Mm-hmm.
This is the part we did last Thursday.
Okay.
Jonathan? Only last Thursday we were doing mass percents. Today we're doing molar ratios. Only difference. So what we are doing, at this point, we have determined the molar ratio between my iron and my bromine. Next thing we're going to do is we're going to determine the molar ratio between the salt and bromine. And for that, we're going to assume that the moles of iron are the same as the moles of the salt. So I've got to find my moles of water. My water weighs 0.621. I divide that by the molecular weight of water and end up with the moles of water. Now I'm going to divide by my moles of iron. I divide this by this, I end up with 5.99, almost 6. So there is a 1-to-6 ratio between iron and water. This means that my overall formula is going to be FeBr3.6H2O. Okay, I've been talking. I need to step back a second and let you ask your questions. Everything seems to make sense? Monica? Kristen, this is making sense to you? I'm hearing crickets. Kyle, we good?
Yes.
Paige? Paige has just left the building.
I've got a quick question about rounding. When we get the final mole ratio, is it just normal rounding? Like if it's above like 0.5, then you round up, and if it's less, you round down?
Excellent question, Kyle, and it depends. It depends upon what you're looking at. If you're looking, perfect question, Kyle. If you were looking at the molar ratio between the elements, this is important, guys. If you're looking at the molar ratio between the elements, you use a integer to multiply them by to get rid of the fraction. So if my ratio between iron and bromine turned out to be 1 to 1.3, I'm going to multiply that 1.3. I'm going to start with a 2. I'm going to multiply the 1 by 2 and the 1.3 by 2. So I can now have a new ratio of 2 to 2.6. Still haven't gotten rid of the fraction. So 2 didn't work. I'll try 3. Multiply the 1 by 3, I get 3. Multiply the 1.3 by 3, I get 3.9. That's close enough to 4 that I'm going to go with it. So I have a ratio of the elements of 3 to 4 at that point. Kyle, you with me so far?
Yeah, thank you.
All right, now, if I am doing the ratio for the salt versus the water, different rules. The salt can never have a coefficient of anything other than 1. So to keep the molar ratio good for the ratio between the water and the salt, that is always rounded. When I'm comparing the elements to one another, the elements don't have to be 1. One of the elements does not have to have a molar ratio of 1. I can have rust. Rust is Fe2O3. Neither one of them has a molar ratio of 1 to something, right? So with the elements, it's important for me to multiply by integers. On the other hand, when I'm dealing with the ratio of the salt to the water, the salt can never be anything other than 1. So if I have something like a ratio of 1 to 1.25, salt to water, well, if I multiply the 1.25 by 4, then I have to also multiply the salt by 4 to have a 4 to 5 ratio, to have the same molar ratio. Does that make sense to you? The trouble is, as I said earlier, the coefficient in front of the salt can be nothing other than 1. So we can't use that little trick when we're comparing the moles of salt to moles of water. When I'm dealing with the water, I just have to round it. So my ratio of 1 to 1.25 would be a 1-to-1 ratio then. Are we good with that? Do you have an understanding of that particular aspect? Because that's the hardest thing for you guys to understand in this lab. Are we good, guys? I need to hear an amen.
Yes.
Not a
Yes,
yes,
sir.
I said an amen. This is a gospel, the gospel according to Mr. Popovich. Come on. I don't
Amen.
even get one amen. Oh my God,
Amen.
I've got a congregation of 0 here. Nothing. I'm getting crickets here, guys. Natalie, give me an amen.
Amen.
Thank you so much. I feel so much better now. So we're going to go on. We're going to do another example of this. I have 2.625 grams of an aluminum sulfate compound with a Z amount of water. I heated and reweighed that at 1.391 grams. The anhydrous compound was put in water and sodium added. 0.5 gram of aluminum was recovered. So I am going to get off of this for a second so that I am going to end show for a second so I can do something magical and take this away. Animations appear. Yay, that's what I should have done before. Okay, slideshow. Now, ladies and gentlemen, I've got everything we need to solve this problem. We need the formula. We need the values of X, Y, and Z. I have 2.625 grams of my compound. I heated it and reweighed it at 1.391. I then took the anhydrous compound, put it in water. I added sodium. 0.5 gram of aluminum was recovered. Abhishek, you hear?
Yep.
Okay. Now, according to my rules, what is the first thing I need to do an empirical formula problem?
Find the mass of the elements.
Find the mass of the elements. So, Abhishek, I've got aluminum weight, I've got sulfur weight, and I've got hydrate or water weight. First of all, Abhishek, there's one that's a gimme here. I'll even give you the gimme, Abhishek. Can you tell me the weight of one of those 3 things, either the aluminum, sulfur, or water?
The 2.625.
Does that give me the weight of aluminum, sulfur, or water?
That gives of all 3.
Gives all 3. There's something in there, Abhishek, that you can tell me right away what the weight is. Paige, can you tell me the weight of any one of those things, aluminum, sulfur, or water?
I don't know.
I don't know is a perfectly good answer. Monica.
There's 0.500 grams of aluminum.
Perfect. We know what the aluminum weight is because that's how much aluminum was recovered. Now, I got to get the weight of the water or the sulfur. I need a volunteer. Can somebody tell me how to get the weight of the water or the sulfur?
Subtract the dehydrated anhydrous weight from the original mass.
I've got the weight of my whole thing, the hydrate. I've got the weight of my anhydrous after the water is driven off. I just subtract those 2 numbers, I'll get the weight of my water. Now, riddle me this, Batman. I've got 2 of the 3. I now need the weight of the sulfur. How do I get the weight of the sulfur?
You would subtract the 1.391 and the 0.5.
The 1.391. I'm sorry. Go ahead, continue.
And then you would get like 0.891.
Okay, absolutely. What we're doing is the 1.391 is the weight of the anhydrous, only the weight of the aluminum and sulfur. If I know what the weight of the aluminum is, I subtract those two, I get the weight of my sulfur. So that's basically what you all told me to do. And I got these three numbers. Now, Alexis, what is the next thing I need to do? I've got the
Turn the
grams of
mass
each of my
to
stuff. What?
Turn the mass to moles.
Going to turn the mass to moles. I'm going to take the mass of aluminum, divide it by its atomic weight, mass of sulfur, divide it by its atomic weight, and I'm going to take the mass of water and divide it by its molecular weight. I've now got the moles of all three things. So what do I do next?
Divide by the smallest.
What? Okay, but I got to do it in two stages. First one, I got to consider aluminum and sulfur. The second one, I got to consider water and aluminum. Okay, so choose one.
Aluminum and sulfur.
Okay, which is smaller? Marlene, which one's smaller? Aluminum's moles or sulfur's?
Aluminum.
So I'm going to divide both of them by 0.0186. I get aluminum to sulfur ratio of 1 aluminum to 1.5 sulfurs. Can I leave this as a 1.5?
No.
So I got to do what?
Multiply them by 2.
There, I'm comparing element to element. So in this case, I have to multiply them by an integer. I start off with 2. I multiply the 1 by 2, I get 2. I multiply the 1.5 by 2, and I get 3. So my molar ratio is 3 to 2. Subscript for aluminum is going to be 2. Subscript for sulfur is going to be 3. Does it make sense, guys, from what you know of naming compounds? What's the charge on aluminum? Each and every time, what's the charge on every aluminum when it's an ionic form?
+3.
3 plus.
+3, and sulfur is?
-2.
-2. So if aluminum is a +3 and sulfur is a +2 or -2, to balance those charges, I need 2 aluminums and 3 sulfurs. It makes sense. Now, if I've got my moles of aluminum and I divide that next into my moles of water, I get 3.6. Remember, I cannot multiply it because the number in front of the Al2S3 has to always be 1. So when I'm comparing water to the metal, I'm going to round that one. So even though it's only 3.6, what I am going to do is I'm going to round that up to 4. So my final answer is going to be Al2S3.4 H2Os. Questions, ladies and gentlemen? I've taken you through 2 of these examples. I've taken you through 2 of these examples. Are you fairly confident you know the math part of this now? Give me an amen. Natalie, you did it once before.
Amen.
Thank you so
Amen.
much.
Praise.
Praise the chemistry. Okay, so when we are doing this experiment, first thing we're going to do, we're going to put a crucible on the balance. We're going to weigh it. We're going to put the hydrate in. I believe it says to use something like 1 gram of hydrate. We're going to put that in. We're going to weigh them exactly. So subtract the two of them. That will give us our weight of our hydrate. We need to heat this gently. What happens if you heat it too hard? You literally will fuse the copper out of the copper salt and decompose it. And you'll ruin both the crucible and your experiment. You're going to heat it. Let it cool, weigh it. Then you heat it again. We did this last week. Why did we reheat it? Why are we reheating the salt?
To make sure all the water is out.
If we get a consistent weight, that means that all the water has been driven off. Okay? We're done reheating now. Now we've just heated all the water out. Now we're going to do something super silly. We're going to put the water back in. The nice thing about this experiment is you can tell when all the water's been driven off, because the hydrate will be a nice greenish blue color. The anhydrous is brown. So when you get all brown crystals, you can be fairly sure that you've driven all the water off. So we're going to put that compound into water, and we're going to make this nice blue solution. Okay? Has anybody ever seen HCl?
In the
somebody
videos,
else.
obviously.
I'm sorry, nobody has seen hydrochloric acid. Has anybody seen pool cleaner, muriatic acid?
Yes.
What color is it?
White.
Clear.
Yeah.
It's clear, right? So if the solution HCl is clear, is the blue color from the CuCl coming from the chlorine?
Yes.
I'll say it again. HCl creates Cl minus ions. So HCl is clear. When I put CuCl in water, it becomes blue. Is the blue color caused by the chlorine?
No.
So therefore, it has to be caused by what?
Copper.
Copper. So I've got copper in solution making the color blue. Keep that in mind. All right, so I've got this blue solution. Now, I've got this blue solution. I'm putting aluminum in there. Aluminum is a more active metal than copper. So because it's a more active metal than copper, the aluminum is going to want to be ionic, which is going to make the copper precipitate out as a brown solid. Now, solution's blue. I'm sorry, I've already said that. We've already gotten that. Let's look at this reaction and think about what is happening. How do I know a reaction is occurring? Two indicators.
Color change, form of a precipitate, temperature change, anything like that.
Absolutely. Who answered that?
Larry.
Good, Larry. Absolutely fine. I'm getting precipitate. I'm getting the copper being formed. It's a different color than aluminum. That's one thing I'm noticing. But also, remember, we said that the copper was causing the blue color. Where's the solid copper coming from? It's coming from the ions in solution. So if the ions in solution are being converted to copper metal, that's taking them out of solution. That blue color of the solution is going to fade. All right, about an hour later, the color of the solution's gone and the wire is covered by a brown solid. I add 6 molar HCl to make sure that the AlCl3 stays dissolved. I get a filter paper, I weigh it, and I knock off all the brown stuff from the wire into the solution, and I pour it through the filter paper. Why don't I use iron Why don't I use an iron spatula?
Because iron would react.
Iron will react with the copper chloride. So if there's any copper chloride, if I use an iron spatula, that also is going to go into the additional weight. I'm going to use suction filtration. I'm going to separate the copper onto the filter paper. I squirt ethanol onto the copper. Anybody know why I'm going to squirt ethanol onto the copper? Has anybody ever put isopropanol on their skin?
Yes.
What's it feel like?
Cold.
Feels cold. The reason it feels cold is that the isopropanol is grabbing water that's on your skin and it's evaporating off. The evaporation process is exothermic. You need energy to get that isopropanol into the air. That energy comes from the heat that your skin is making. Your heat goes away from your skin, it feels colder. So basically, I'm squirting ethanol on there to make sure that I get evaporation. The ethanol will dissolve on any water. It evaporates the water that much quicker. So then I get the filter paper, dry it, and weigh it. Whole experiment. That's it. Now, in the calculations, we made an assumption. For extra credit, I gave you 5 points on it. Put the answer to this question in the, there's that one box that says basically you never put anything into it. Basically, put the answer to this question in that box. You will get 5 points extra credit, up to the value of the entire results section being 60. Your value will not go over 60.
Is there more than one possible answer to that? Because I can think of a good one right now.
Talk to me after class.
Okay.
I can only think of one. Okay, I am not talking about experimental errors. I'm talking about an assumption you made in the calculations.
Okay.
Okay, that is the end of the slideshow. Now what I'm going to do is I'm going to take you through the, if I can find it. Guys, is this doing you any good for me to go through the results in the post lab with you?
Yes. Yes.
It does.
Because
Yes.
if it's not doing you any good, I might as well cut you loose now. I just kind of like to give you a preview of upcoming attractions. Don't look so bored, Kyle. Kyle, I'm kidding. All right, first question. Mass of the hydrated sample. Second question, mass of the dehydrated sample. We've been through that. I gotta move you guys. Second question, mass of copper, number of moles of copper. Third question, mass of water, moles of water. Mass of chlorine, moles of chlorine. Mole ratio, copper to chlorine in sample, I'm sorry, chlorine to copper in sample, and put it in that order. Mole ratio, water to copper in hydrated sample. Put it in that order. If your order is reversed, I will mark it wrong. I'm sorry, but I have to. And this is the box that you answer the extra credit in. Fairly straightforward, guys. Is there anything you have questions on in answering the results?
When we're calculating the moles, how do we do the short verbal description?
Okay. Easy enough. Part B here, what I would do is I would put 13.54 parentheses grams of chlorine times 1 mole over 35.45. That's enough for me to know that it's the atomic weight. You don't have to put atomic weight of chlorine. I think after, let's see, I've been doing this since I was 16. So I think after 48 years, I know the atomic weight of chlorine. So just label the grams of chlorine and then the final answer as moles of chlorine. Fair enough? I don't know who asked the question.
I did. Thank you.
I'll say I did. You know how many I dids I have in this class right now? I did is must have been a very popular name in 2003 for children. I have a ton of I dids in class. Who was it? Come on.
Garrus.
Thank you. Thank you very much, Garrus. Any other questions about the results? Okay. Getting back to course content. And, okay, we're okay. Post lab. Okay, and we're going to go full screen. Preview. Start quiz. A certain compound contains copper and oxygen. We find that a sample weighing 0.7378 contains 0.3929 grams of copper. How many moles of copper are there in the sample? Second question. You have copper and oxygen, only copper and oxygen. A sample that weighs that much contains that much copper. How many grams of oxygen are in the sample? Okay, you have that much copper, that much oxygen. How many moles of oxygen? Note, guys, the numbers are changing. If you notice this, it would have been real nice for him to keep the numbers the same. He chose not to. So do not carry your answer from one problem to the next. You got two elements. It's found to contain that many grams of X and that many grams of Y. You are given atomic masses. Find the molar ratio of Y to X. Again, make sure that you're reporting it in that order. Also, he wants the rough molar, I want the rough molar ratio. Okay, I want the rough molar ratio there. Second question, next question, you got 0.1 grams of carbon. You have to assume that that C is carbon and not just a letter. Carbon and 0.1500 grams of water. Determine the mole ratio of carbon to water. Any questions, ladies and gentlemen?
When you say the rough number, does that just mean the three
Okay,
decimal places?
yeah, like for example, if you do the molar ratio carbon to water here, your answer may end up being 2.15, 2.156. Okay? He wants you to report out to 2.156. He does not want you reporting out 2. Does that make sense, guys?
Yes.
If you don't report it out to 3 decimal places, it will be marked wrong. So give him the answer that he wants. 3 decimal places, 3 decimal places. This one, he's not saying, but I've got 4 digits and 4 digits. How many significant figures should your final answer have?
4.
There we go. Any other questions, guys? Okay, those of you that have me for lecture. Oh, actually, I want to ask this question of the others of you. This is just for me, my own benefit. How far are you along in lecture? Tonight, I'm doing empirical formulas. Are you further along or are you catching up to me? Come on, somebody. What?
No, I don't. We're definitely not at empirical formulas.
Okay. Anybody else? Does anybody have Dr. Musgrave? Is he? I don't even know if he's teaching it this semester. So you guys are not on empirical formulas yet. Shake your heads. Do something. You have no idea what I'm talking about when I'm talking about this stuff. Okay. If you have any questions on me, feel free to stay after. Other than that, this ends my presentation.
Have a great day, Professor.
You have a great day too. I'll see some of you at 5:30.
Bye. Have a good one.
You too.
I have a question.
Who is speaking?
Marlene.
Marlene, what's going on?
So do you post these recorded videos or no?
Yeah.
Where are they? Because I couldn't find it.
Amazingly enough, it's in a module labeled Zoom meetings. Somebody sounds like they just had a smoke alarm go off. That chirping sound that when your battery dies. I just had the irritating thing to do that this weekend. Okay. Marlene, are you seeing me? Are you seeing the screen?
Yeah.
You see Zoom meetings?
Yeah.
Got to click on that. Then you got to go all the way. I know it's a pain in the butt, but you got to do it. Then if you click on this, what you're going to get is a Word document, but this has clickable sites. So literally speaking, all you got to do is focus on it, hit Control, right click or left click, and sometime. All right, I got to stop share screen. There you go, Marlene.
Okay, thank you.
Okay, good enough. Now we will get, no thanks. We will get you guys moved so I can click that off. Stop share. Okay. Corey Jeremiah Garris, do you have anything?
Yeah. Okay. So for the lab book, with the chemical hazards, do you want us to write the
Copper
chemical
chloride.
that?
Copper chloride.
Yeah.
Yeah, that's about it. Copper chloride.
Okay, just
HCl.
copper chloride.
HCl. You're using HCl too.
Okay.
Okay. Here's something, guys. If you encounter a hazard in the future, like this is not the last time we're going to be using HCl. then all you have to do for the hazards is say, please refer to experiment such and such. Save yourself the time. Okay? Make sense?
Yes.
Anything else, Garrus?
And in the conclusion, we don't have to do any calculations, right?
Well, the calculations go where the calculations.
Well, the calculation, yeah. I think what
Well, I'm
Garrus was
talking about like
asking is
standard deviation and percent error.
Percent error. I could make you do it. You could do it because no, I'm not going to make Garrus. If this was an actual experiment, it would make sense to do that. Okay, but it's not. Okay, I could make you say, okay, your molar ratio between copper and chlorine is, you came up with the rough ratio of 3.13. The right ratio should be 3. So you could technically do a percent error of that rough ratio. Does that make sense? I'm not going to make you do it. All right.
Okay.
I can't think of any calculation you'll need to do in the conclusion. Jeremiah, Corey, anything?
I was just gonna make my guess for the.
Okay. I'm gonna need the other two off. Unless the other two want to venture a guess themselves.
I just had a question about the calculated data for the formula of dehydrated sample and the formula of hydrated sample. So we've calculated the mole ratios. For the formulas, you're actually just talking about the formula itself, like that information put to use.
Yeah, basically for like the mole ratio between the elements, between the copper and the chlorine, you're just going to give me what the final mole ratio is going to be.
Gotcha. Okay.
Like for example, if it works out to be that the mole ratio was 1 to 1.5, then the formula would be the first one 2, subscript 2, the second one subscript 3. Are you understanding? I jumped some steps there, Jeremiah, but are you understanding what I'm saying?
Yeah. Do you want it formatted like with the element out front of the ratio itself? So for example, if it says like copper 2 hydride, you don't want, number of copper to that. You want it actually like Cu and then the atoms, for example.
What you're going to do, say for example, the molar ratio between your copper and chlorine was 1 to 3. And your mole ratio between your copper and your water was 1 to 4. For the entire formula, you would write Cu, no subscript because it's assumed to be 1, Cu Cl3 dot 4 H2O.
Okay.
Does that make sense, Jeremiah?
Yep, that makes sense. Thank you.
Anything else?
I have a question. So if that was the dehydrated sample, it would be the same thing, but without the H2O?
Correct. Cu, that would be Cu Cl3.
Okay.
No water. Anything else, guys? Okay, Garrus and Jeremiah, get off. I'm going to stop recording right now.